This video is continuing the example from 1.7 and repeating it for a sample with the same dimensions, but now a Poisson's ratio of 0.5. So, in this example, it is the same loading, which is an axial load of 1,000 pounds, and the same original dimensions. So with all that being the same, the cross-sectional area has to be the same. We already said that the load, axial load P, is the same. So therefore, given that axial stress is the axial load over the area, that has to be the same at 4,000 psi. Now, remember, because the load is in the axial direction, so that means that this is an axial stress. The axial strain, or epsilon sub AX, is determined from Hooke's law, and in this case we rearrange that to be epsilon strain equals sigma stress over Young's modulus, capital E. So 4,000 psi over 10 million psi is the Young's modulus. That gives you a strain of 0.004, which is the same as before. That stands to reason. The cross-sectional area is the same, the load is the same, and the Young's modulus is the same. The thing that is different in this case is the Poisson's ratio, which is the relationship between the axial strain and the transverse. So we're still talking about in the axial direction, so since that axial strain is the same, the new length after this load is applied has to also be the same when you have a 0.004 strain applied to a 10-inch structure. You're going to have 0.004 elongation. So our L prime is 10.004 inches. Now, that's all in the axial direction. Because our Poisson's ratio, nu, is different, the change in width and change in thickness will be different. So generally, the transverse strain is equal to the negative Poisson's ratio times the axial strain. In this case, our Poisson's ratio is 1/2. So we have our negative 1/2. Our axial strain is our 0.004. So our transverse strain for this case with this Poisson's ratio, half of that, 0.0002. Alright, we now know what our strain is going to be. We use our strain to figure out what the change in width and the change in thickness are going to be. Change in width is in the transverse direction, so that's the transverse strain times the original width The original width in this case was 1 inch. So easy math in that case is 2/10,000ths of an inch. Your new dimension is equal to the old dimension plus the change in the dimension. Originally the width was 1 inch. If we lose 2/10,000ths, we end up with 0.9998. Similarly, the change in thickness the same transverse strain, this time times 1/4 of an inch is, well, 1/4 of the dimension change, and new thickness is thickness plus the change in thickness. Our original was 1/4 of an inch, 9.95 inches. Okay, we have all three of our new dimensions. We need to now check the volume. New volume is new length times new width times new thickness. 10.004 times 0.9998 times 0.24995. All of that ends up as inches to the inches cubed. And if you carry out and do the math with all the decimal places, you see that it is in fact 2.5 on the dot. So the interesting thing here is that there is in fact no change in volume when Poisson's ratio, nu, equals 0.5. What does that mean? That means that this substance is what we call incompressible, or a Poisson's ratio of 0.5 is what defines an incompressible material. Okay, this next little section is going to take a little bit of mathematical formalism to talk about or show how this Poisson's ratio nu of 1/2 ends up being no volume change. Generally, a change in volume is, or the new volume is the new length times the new width times the new thickness. Well, if we look at any individual one of these, for example, a new length is the length plus the change in length. Well, we know that the change in length, that's in the axial direction, so the change in length has to equal the axial strain times the length, and we can also say that that equals the length times 1 plus the axial strain. By this same argument, we can say that the new width is the width times 1 plus, this time it's the transverse strain, and, the new thickness is the thickness, original thickness, times 1 plus also the transverse strain. Okay, so we can put all of these together and say that we've got the length times 1 plus the axial strain, taking that as a quantity, and we've got the width times 1 plus the transverse strain times the thickness times 1 plus also the transverse strain. All of those, the product of all of those terms is the new volume. Okay, well, rules of multiplication allow us to pull the length, width, and thickness terms. So then that leaves us with 1 plus the axial strain and 1 plus the transverse strain squared, which is 1 plus 2 times the transverse strain plus transverse strain squared. So, when you have itty-bitty numbers like a transverse strain, and you have the product of itty-bitty numbers, the product of two itty-bitty numbers is an even smaller number. So those can be considered negligible. So we get rid of our squared term based on the fact that it is another orders of magnitude smaller. And we can say that we've got length times width times thickness times 1 plus axial strain times 1 plus 2 times the transverse strain. But from our definition of strain, we know that the transverse strain is the negative of the Poisson's ratio times the axial strain. So we can use this here. So we now have our new volume cast in terms of just the transverse strain. We can rewrite and do just a little bit of algebra. Length times width times thickness times 1 plus axial strain times 1 plus 2 times minus Poisson's ratio times axial strain. Just a little bit of rearranging of this lets us say that it is 1 plus axial strain times 1 minus 2 times Poisson's ratio. Now, when we look at this term right here, when Poisson's ratio equals 0.5, we have 1 minus 2 times a half, and that term goes to 0. That term goes to 0. That eliminates the axial strain, and you have simply length times width times thickness times 1. So V prime equals length times width times thickness. Length times width times thickness is the original volume. So the new volume equals the old volume. Materials with Poisson's ratio of a half are incompressible. No volume change under axial deformation.